Okay, next we're going to talk about taking the derivative of an exponential function. There's a difference between what we just talked about and the exponential function. We talked about earlier the power function. So a power function, just make note of the difference between the two here. The power function looks like this, where you've got x raised to some power, like 4. And then we could take the derivative by bringing the 4 down in front and then decreasing by 1 for the power. An exponential function looks more like this, where you have a number of some sort raised to a variable power. That's an exponential function, and its derivative is a lot different. So the derivative of an exponential function, or you could write it this way, is b to the x times natural log of b. A more familiar exponential function is e to the x. The derivative of e to the x, kind of following the same pattern, is e to the x natural log of e. But if you remember a little bit of algebra, or if you don't, type it into your calculator, the natural log of e is just the number 1. So this is just going to be e to the x times 1, or e to the x. So the derivative of e to the x is e to the x. The derivative of any other base to the x power is that base to the power times natural log of the base. We're going to go through a little bit of a proof of that. The proof isn't quite as important as just knowing what's the natural, or what is the derivative of b to the x, for example, but we're going to show how this is. E is a number, and the definition of e is the limit as h approaches 0, or not the definition of e, but using that, the limit as h approaches 0 of e to the h minus 1 over h. Now we could find this by doing our numbers, plugging in and doing a numerical analysis, because if I plug in 0, I'm going to get 0 divided by 0. This isn't something you can factor either. So this comes from sort of numerical analysis. Plug in numbers very close to 0 on the left and the right and see that the answer comes up 1, or type this function into your calculator, y1 equals that, and you'll see that as h approaches 0, your values approach 1. So using this definition and the definition of derivative, we're going to find out what is the derivative of b to the x. Keep in mind we already saw what the answer was, but if we use our limit definition, remember it's the limit as h approaches 0 of, and then it's just kind of going back to the definition, f of x plus h minus f of x divided by h. Our function is b to the x. So where there's an x, I'm going to be putting in x plus h. Keep including the words limit as h approaches 0. So this is b to the x plus h minus b to the x, all divided by h. All right. Well, this is a little strange, but if I have b to the x plus h, using laws of exponents, I can work backwards from it and call it the limit as h approaches 0 of b to the x times b to the h. When I multiply like bases, I add the exponents. So I just went in the other direction. If I'm adding the exponents, I'm multiplying like bases. And the reason for that is now I can factor out b to the x. So if I factor out b to the x, I'm left with b to the h minus 1 divided by h. All right, this b to the x has nothing to do with h, so it can go out in front of the limit. And then as the limit is b to the h minus 1 over h as h approaches 0. All right. Well, when we did this one, up here, another name for e is, or another name for 1 is natural log of e, and that's with a base of e. Our base is b, so when we rewrite this, this is going to be b to the x, and instead of an e in here, natural log of e is 1, it's going to be natural log of b, our base. So again, it's just showing that the derivative of b to the x is b to the x natural log of b. All right, so we're going to go through a few examples here just to take the derivative of these functions. Keep in mind, we're using our shortcut method. We're not using the definition of derivative because that would be a hot mess. But we are going to go back and make sure that we don't have variables in a denominator. We're going to make sure that we don't have any roots in our function. So before we get started in taking a derivative, let's clean up the algebra first. All right, so x to the 7 is cool. 7 to the x is fine. 7 divided by x, I'm going to move the x up to the top, change the sign of the exponent. The exponent where it is positive 1. When I move it up, it becomes negative 1. E to the 7th is fine. And then plus, and then this is 1/7 x. I didn't do a derivative at all, so I'm still talking about the original function. Now I'm going to go through and take a derivative by using my power rules. So I have power and exponential rules. So this is a power. I can pull the power down in front, decrease by 1. X is not a power, or it's in the exponential position, so this is an exponential function. So this is going to be the derivative of, put the minus down, the derivative of 7 to the x power is 7 to the x, natural log of 7. Right? Bring the power down, multiply it times the number in front, and then decrease. So subtract 1 from minus 1, that's going to give you a negative 2. E to the 7th. Don't get too quick here with pulling that 7 down because e is a number. It's not a variable. So that's not a power function. That's a constant. That's going to be the derivative of e to the 7 is 0. The derivative here of 7x to the 1, if I pull the 1 down in front, this is just 1/7. And then x to the 1 minus 1, or x to the 0, which is just 1. Usually we'll let students leave it here. If you don't want negative exponents, then that's going to slip down. So your derivative could look like this. And it would be 7x to the 6. And again, I don't need to leave that plus 0 in there either. So minus 7 over x squared, and then plus 1/7. Okay. All right, so let's take a look at example 2. Differentiate the following here. And again, you're looking for, do I have any radicals that I need to rewrite as a power? Do I have any variables in a denominator? And in this case, you don't. So our variable is t. So we're going to find g prime of t equals. This first term is an exponential. It's e to the, like an e to the x, only it's e to the t. So the derivative of e to the x is e to the x. The derivative of e to the t is just e to the t. Constant stays out in front. T to the e. All right, e is like 3, like it's a number. All right, well, it's not 3, it's like 2.7 something, but it's a number. So this is a variable raised to a number. We're going to pull the number down in front and then decrease by 1. We're keeping it exact, so don't switch e to the number part. And then log base 8, that's a number. That's a constant. So when you take a derivative of a constant, the answer is 0. This would be your final answer. and then the slope of the tangent line at x equals 1. So we're trying to figure out what is h prime of 1. H prime is slope of a tangent line. Remember, that generates a whole bunch of formulas, but then we're interested in it specifically at 1. So I need to find h prime of x first. But before I do that, notice there's a whole bunch of stuff going on here. There's a bunch of parentheses. I need to FOIL it out first before taking a derivative. Remember, I can't take the derivative of one thing times the derivative of another. That was a no-no back on the previous page. It had, you can't break it up. You can't break up a derivative if you've got multiplication or division. So we're going to first do the algebra, keep it as h of x, FOIL it out. So this becomes x to the 5th minus 6x cubed, and then plus 3x cubed, and then minus 18x. Right, so clean it up. So we got x to the 5th minus 3x cubed minus 18x. Now go ahead and take a derivative. All right, so power rule, pull the number down in front, decrease by 1. Pull the number down in front. There is a number in front, so we got to multiply 3 times 3 and decrease. Pull the number down in front and then decrease, but x to the 0 is just going to be 1. So from here, go ahead and plug in your number 1 and then evaluate. So I believe you get negative 22. And negative 22 is the slope of the tangent line at that particular point. And so if you were to graph this and then look at x equals 1 on the graph and then draw in the tangent line there, that's the slope that you would see. For example 4, again, taking derivatives with a quotient, you don't want a variable in the denominator if you plan on using the power rule. So let's simplify using algebra first, then we'll go ahead and do the calculus. So I'm going to pull, well, let's do this in a couple of steps. I'm going to rewrite the cube root of x as x to the 1/3 power over root. I'm going to move this up to the top and multiply by the numerator, the x to the 1/3, and it's going to be x to the negative 1/3 when it comes up. Cross the line, change the sign. Okay. So now distribute so that we just have some sort of function in standard form, getting rid of parentheses. And this is where, if you're not great with adding fractions and whole numbers, then get your calculator out. When you multiply like bases, you add the exponents. So my k of x is going to be x to the 8/3. Where did she get that? Negative 1/3 plus 3. Use your calculator. Minus 2 times x to the 1 plus the negative 1/3 is going to give me x to the 2/3. And then x to the minus 1/3 times 9, x to the minus 1/3. Keep all the variables up in a numerator, then I can go ahead and take a derivative. And so if I do the derivative, I pull the 8/3 down in front and decrease by 1. So subtract 1 from 8/3, or subtract 3/3 from 8/3 and get 5/3. Pull this down in front, multiply 2 times 2/3. and then decrease by 1. So take 2/3 minus 1, negative 1/3. Pull this guy down in front, multiply negative 1/3 times 9, and then again, decrease by 1. So negative 1/3 minus 1, and get negative 4/3. The calculus is not hard. The arithmetic will screw students up. So make sure that if you're not great with your fractions, get good with your calculator and convert back to fractions. Let's